Welcome back. Let us resume our discussion on cascode amplifier that we started last day. So we have looked into single stage, single ended cascode amplifier where the input signal is applied at the gate of M1 and the output is taken at the drain of M3 and M2. You have some appropriate bias point over here. We also saw one easy way of biasing the gate of M4 and M3 so that you can get an appropriate signal swing over here. And we also analyzed the output signal swing, what is the maximum and minimum output signal swing. In order to arrive at this, before that we looked into the small signal impedances, looking into the drain and source of the MOSFET under different loading conditions, and we derived the expression for that, which was useful in understanding the operation of this cascode amplifier. And what we concluded, the basic conclusion out of this was that in single stage we are able to get the gain GM-RO whole square, which is comparable to the gain of the two-stage op-amp that we use, open loop gain of the two-stage op-amp that we get. We also looked at the poles. So here we saw that the output pole is going to be the dominant one because here the impedance is GM-RO square, GM times RO square, which is much higher than RO. As a result, this becomes the dominant pole. Other two are having an impedance just given by RO. So as compared to the two-stage amplifier where the two poles P1, P2 are comparable, here we have a dominant pole. One of them is already dominant and it is having a value GM-RO times lower as compared to the other one if I just depend upon the parasitic capacitances. And therefore, if I have to compensate the closed loop operation involving such amplifiers, I would like to just compensate this dominant pole. I would like to just push it towards further lower frequency and obtain a overall phase margin of 45 degree. So that is one of the advantage of this stage. You are having self compensation. One of the poles is already dominant and you want to just push it by another significant factor so that it goes down. You are getting a larger gain. The overall gain is comparable to the two-stage. The disadvantages, as we discussed, was the swing. The input as well as output signal swing will be limited. So output point of view, we saw that the best that we can do is to get overall swing of VDD minus 4V over drive. That is the overall peak to peak that you can get, because what we saw is that the maximum side V out max that you can have, assuming that these gate voltages are in our hand and you can set them. So V out max that we arrived at was equal to VDD minus, and V out min that we can have is simply 2V over drive of NMOS. So this is the minimum and maximum output level that you can have, provided I have the freedom to control the gate voltages. Therefore, if I look at the overall swing that you have, V out max minus V out min, we have V over VDD minus 4 V over drive. And V over drive, depending on the bias current, it can be few tens of millivolt to 100 millivolt in this application. Especially if you're trying to get better gain, in that case V over drive can be reduced by having a lower bias current and having a larger W by L. And once again, there is going to trade off with other parameters like the bandwidth. We will see that the V over drive is also having a strong trade off with noise. So when we do the noise analysis for the cascode amplifier, we will see that it is also going to have a significant and an important trade off with noise of the cascode stage. So we looked at a simple biasing scheme where we bias the PMOS stage with the help of current mirrors, a cascode current mirror. Likewise, we looked at the biasing of the gate of the M2 also. So that was not the best case. The best case would be to have the DC bias point at the gate of M2, which is the lowest possible. Likewise, have the gate voltages of M3 and M4 which are highest possible, because if I keep the gate voltages of M3 and M4 highest possible, then I can get the maximum possible output swing over here. The output V out max can be highest possible. Likewise, if I keep the DC bias voltages at the gate of M2 to the lowest possible value, I can get the V out min to the lowest possible value. So in order to minimize the V out min, I would like to keep the gate voltage of M2 to the lowest possible, and I would also like to keep the gate voltages of M3 to the highest possible value so as to maximize V out max. That was a summary of the discussion that we had last day on signal swing. So, just to recall, the VG2 min that I can have is going to be VG1, the DC bias at the gate of M1 minus VT of M1, that is basically the minimum drain potential that you can have at the drain of M1, and hence the potential at the source of M1, that plus VGS. VGS, I am assuming VGS is same for all, provided W by L are same. To be clear, I can just write it plus VGS2. And likewise, I can determine the maximum gate potential for the M3 required or allowed. Now, once I have this VG2 min, that would imply that the potential over here is VG1 minus VT. So, if I force this DC potential equal to VG1 minus VT1 plus VGS2, then I am assuming that the potential over here is the minimum allowed potential at the drain of M1, which is VG1 minus VT1. And the assumption there is that signal swing over here is much smaller. Even over here, if it is close to 1 volt, here it is going to be 1 upon 100. So, 10 millivolt or smaller than that. Therefore, the swing is not a major constraint, even if this is biased at the edge of triode region. That means, the DC potential over here is equal to VG1 minus VT edge of saturation. Below that, it can enter into triode. So, I am happy with that, because assuming that the signal swing over here is very small and is not going to push this in triode. Signal here is weak. So, this is the minimum drain potential that I can have for M1, and then corresponding to that, I can see what is the signal swing that I am allowed to have. Now, signal swing over here of course depends upon the overall signal swing over here in the open loop case. So, if I am just using this amplifier in the open loop, I do not worry about signal swing, because the signal swing over here will be dictated by the maximum signal swing over here divided by the gain. Maximum signal swing is maybe 1 volt for 1.8 volt supply. Suppose you are able to get a 1 volt, which is not very difficult to obtain, and that divided by the overall gain GMRO whole square by 2, which is pretty large. It can be several thousands. As a result, the input signal swing that you are allowed to have possibly millivolt or lower than that. So, that is the allowed. This is how I can find out the allowed input peak to peak swing, maximum output swing divided by the overall gain for the open loop case. But when we look at the differential operation and try to apply such a high gain single stage amplifier in feedback, then of course, the closed loop gain will be smaller. This stage will be just providing as a mechanism for building a high gain op amp, through which we can realize closed loop systems with well defined gain. In that case, of course, the input output gain will be limited, maybe few tens or 100 at the max. In some cases, when you are using this as a voltage follower, the gain from here to here, closed loop case, can be just unity, and in those cases, of course, the input swing becomes important. And what we can see here is that input swing will be severely limited, because you are having the DC potential over here pretty small, VG1 minus VT1 in this example, and therefore, the maximum potential that you can have over here is just going to be VG1, the minimum DC potential here plus the VT of this. So, it will be very small swing allowed over here if you are trying to push this to the minimum value. So, in that case, it will not act like a good voltage follower, or it will not be able to cater to closed loop gains which are limited, maybe few tens. So, we need to take care of the closed loop operation if we are applying the differential scheme for this cascode for realizing op amps and building feedback amplifiers with the help of this high gain stage. Let us straight ahead go to the differential scheme, which should just imply that we use another alternate branch, the differential branch, and put a current source over here, just like we do for the simple common source stage. So, just like in the common source stage we club the two differential pairs, I am just going to do the same for this one. So, that would imply that I have the cascode branch and the input branch and along with that I have the tail current source. So, this is a possible scheme. Now, these two gate voltages they can be biased with the help of some common mode feedback scheme that we can discuss, just like we do it for our normal differential amplifier with active load. and again I need a proper bias point over here. So I need a proper bias point for these devices, and also I need to set up the bias point at the gate, and then I have my outputs over here, VO minus and VO plus, if this is the VI plus and this is the VI minus. So this is the corresponding differential scheme for the cascode stage, and once again the analysis boils down to the similar process that we have for the differential amplifier analysis. For the differential gain, you will just put this as AC ground and then find out the gain from the input to the output, which is just going to be GMRO whole square by 2, and therefore the overall gain, differential gain, VO plus minus VO minus upon Vin plus minus Vin minus is GMRO whole square by 2. So the analysis for the differential mode remains more or less similar. Only thing is we have to look at the other considerations: frequency response, swing, bandwidth, etc. Now whatever we discussed with respect to the frequency response and the bandwidth, that remains more or less same, but is whatever is applicable for the single ended case, because for frequency response, once again this is AC ground for the differential operation. You have a dominant pole over here and non-dominant pole at these 2 points, and if I am using this particular circuit for closed loop operation, I would like to compensate the output node over here directly, because this is a dominant pole. I would simply like to put some more capacitor over here so that the dominant pole gets shifted further towards lower frequency and I can get a better phase margin. So here we have the dominant pole compensation coming into picture. So here we are not going to rely on Miller capacitance, we are not going to use Miller compensation, but going for dominant pole compensation. So you are having the first pole P1 and the second pole P2, where I already have, say, without any compensation, I have the P1 coming over here and the P2, the 2 P2 poles here, and I can call this also P2. They are going to be relatively close, because what we discussed over here, the impedance at these points are almost similar, and as a result the capacitances are also similar because they are coming from the parasitics of the devices. I don't have any additional capacitance put over here. So these 2 points are going to have similar poles in the overall response, and so I can just put them as P1 and P2, and then I can look at the ratio. The ratios of these 2 poles, if I don't have any additional capacitance put, is going to be of the order of GMRO, because we know that the impedance over here are of the order of GMRO. So this may be P2 upon GMRO. And in the closed loop, if you are trying to build a closed loop amplifier with the help of this, I would once again like to have the P2 to be much lower than P1 by the factor of GMRO whole square. This is the overall gain. So I need that P1 times the GMRO whole square, that is the open loop gain of this amplifier, equal to P2. So I need to put an additional capacitance of this value GM, or I need to make sure that the capacitance ratio over here, the parasitic capacitance upon or the ratio of the added capacitance over here upon the parasitic capacitance over here is also having a ratio of GMRO. So whatever additional capacitance I put at these nodes, I can call this CC, or it can come from the load capacitance of the next stages. There I need to make sure that the ratio of this CC and the total capacitance over here is close to the GMRO factor, and it is not very difficult to achieve. If I look at 180 nanometer technology, for example, 1 micrometer width device, 1 microchannel length and 1 micro width may provide you total parasitic capacitance close to, say, a few femto, 1 femto around. And as a result, if I say, even if you are using a larger devices, say few tens of micro, so the overall capacitance, parasitic capacitance over here can be close to few tens of femto to 100 femto. It will not be more than that, close to that range. So a small fraction of picofarad. As a result, if you want to make this, say, GMRO times this, where GMRO is, say, 100 or larger than that, I can use a few picofarad capacitance over here, so that it is easily, say, 100 times larger than the parasitic capacitance coming over here. And I may not even need to put a separate CC, because if you are having multiple stages and next stage is having a capacitive input like we did for our front end amplifier, So the Cc will be basically coming from the input capacitance of the next stage, where the gain is determined by C1 upon C2. So this will be basically C2 of the next stage, which is automatically giving me the required compensation capacitance. So that way we can say that this is self-compensated. This cascode amplifier is having the property of self-compensation. You don't need to worry about the insertion of Miller capacitance, which leads to other complications. We have discussed other complications related to arising of zero, and then we need to figure out techniques to cancel out those zeros by inserting buffers or by inserting the nulling resistor, which again has to be controlled. So it leads to a lot of complications definitely, but here we see that it is able to self compensate and mitigate the instability issue. And of course, one of the limitation that we have seen is that the output swing is relatively limited in this case. Now, once you have added this tail current source, output swing gets further limited, because now this is not longer at source. You need another V over drive voltage for this current source. So if this is Vg, Vg of the current source, Vgc, the minimum voltage here that you can have, the minimum absolute voltage here you can have is Vg C minus Vt. That is basically V over drive, right? We call this term V over drive, which is Vg minus Vt, Vgs minus Vt. So here once again I have another V over drive added, and we know that for the stack we have another 2 V over drive. Therefore, the minimum level that you can have over here is going to be 3 V over drive, and on the upper side VDD minus 2 V over drive. So again the swing is getting further limited, output swing is getting further limited, and once again, if you are operating this as feedback amplifier, then the input swing may need to be close to output swing, for example, a unity gain buffer, where the input outputs are changing the same fashion, or even if you are having a relatively smaller gain factor of say just few tens, in that case the input swing may be just around 10 times smaller than the output swing. Output swing is say target swing is 1 volt peak to peak. So here I want at least say around 100 millivolt input range, and with 1.8 volt supply I have to make sure that the input swing is the required input swing is achieved. And apart from that, input common mode range is another important factor, where the input DC level of this stage may be coming from some other stage, and if in a cascade of analog stages the input DC level of this point is coming from some previous stage which can change over time, I need to make sure that the input common mode range, or that is basically the range of input DC bias point that this amplifier can tolerate, that should also be sufficiently large so that it is able to tolerate any change in the input common mode DC level. In our example that we are dealing with, we have anyway stated that the output DC common mode is being determined by common mode feedback if it is a fully differential case, if it is a fully differential operation, and then with the help of that we are fixing the input common mode level. If we do that here, once again in that case basically we will be pushing the input common mode DC level or input bias point close to the output DC level. Now output DC level, if we look at it in this particular example, we are seeing that the maximum signal swing in this example V out max that you can have at a single end is equal to say VDD minus 2 V over drive, and the V out min that you can have is V over 3 V over drive, basically V over drive of these two transistors plus this one. So of course they are not equal, because it's not necessary that the current and the W by L are equal. Here we can say that the W by L and the currents over here can be different from that of this one, but I'm just taking this number V over drive as a common factor, is around 3 V over drive, and this can be 1.8 volt minus overdrive, even if it is 0.1 volt or it can, or 0.15 volt, it can lead to 0.3 volt over here, and the maximum maybe around 0.3, so 4.5 volt, sorry 0.45 volt over here. So you are having from 1.5 to 4.5, and therefore we can say that okay, 1 volt can be achieved, 1 volt peak to peak can be achieved, and then I would like the output DC point to be close to midway of this. So we are seeing that okay, the output DC point for a 1.8 volt supply can be close to 1 volt. So I would like this to be 1 volt, and then in that case, if I try to apply that same 1 volt over here, means using our earlier scheme where we are using resistive feedback, and try to apply the same 1 volt over here, whether this is going to be a good bias point for this one. There we can see that if we apply 1 volt over here, then basically this potential we were trying to keep it at the minimum allowed DC level, so that I can have maximum possible swing, right. So, if I have if I look at my minimum allowed DC potential that I arrived at, what was that? That was the Vg minus Vt plus Vgs, and Vg minus Vt once again, because it is low current biasing. So, the Vg minus Vt can be close to say 0, maybe 0.1 volt or something, and then you have Vgs, which is again close to Vt. So, that is again going to say 0.5 volt. So, 0.5 volt plus 0.1, so it is around 0.5, 0.6 volt. But if I am allowing, so the V in, I would say V in Cm min that I have estimated is around say 0.6 volt. This is the estimated value in order to allow maximum possible swing at the output. But if I use the output DC point in this case to bias my input DC, then I am going to have midway of this. So, desired output DC point at the output is 1 volt in order to allow that maximum swing, and I am going to allow that over here by that large resistor, and that definitely is much higher than what I want for best swing at the output. So, it is not going to serve the purpose of having best possible swing at the output, because I cannot apply the relatively higher output DC level over here, output DC common mode level over here for biasing the input DC common mode for my input pair. Therefore, this may not be a very good scheme. I may have to go for some alternate biasing scheme for the input and complicate my design further. So, this is one of the main issues. The DC biasing for the input can become problematic for our application, and in general, if you are looking for feedback operation where you are having a voltage follower operation, there also you can see that ultimately the DC point at the output will be affecting the DC point or setting the DC point at the input. So, you cannot even build a good voltage follower using this scheme. And in our particular example, the main concern is that we are setting up the bias point over here with the help of output common mode, which is not very feasible here, because it is going to drastically affect our swing. This point is clear what we are trying to mention over here. So, the good points with this scheme, with this particular circuit, is good differential gain. In a single stage you are getting GMRO square, self compensation property, with the help of which without even adding very significant, very large capacitance, you are able to achieve a good phase margin, and we will see that you can the on the other side, the negative points that you have is the limitations on output swing, and more severely the input biasing. How will you use the output DC common mode for maximum symmetric swing to bias the input DC. There are some other advantages also, like we have discussed the concept of PSRR, power supply rejection ratio. There the cascode devices do have advantage as compared to our two-stage op-amp, that we have not discussed in detail. Probably in one of the classes we will try to address that as well. So, any question before we try to look at alternate scheme, which is a folded cascode scheme, which can resolve this issue of DC bias and the swing, at least the input swing. And then also we have to look at biasing scheme through which we can get best possible output swing. So, there are the next discussions looking at the folded cascode topology, where the constraint on the input swing and the input DC biasing is resolved, and second the output swing considerations, where I need to set up the appropriate bias point for these transistors so that my output swing is maximized. And once again we can look at both the topologies, the single ended output one, just like our differential amplifier with current mirror load, where you have single ended output, and the second one where you have fully differential output and you need a common mode feedback. Any question before we proceed further?
Can you explain once more why 1 volt input supply DC is not suitable?
Yeah, so what we said is that if you look at the minimum allowed DC potential that we found out for this. Why did we found out minimum allowed DC potential? Because if you put the minimum allowed DC potential, then only you can have maximum allowed swing. If you put this DC potential or the DC bias lower and lower, it will allow the output V out min to be lower and lower. So, we from our analysis earlier, we found out that V in Cm min, that is the input DC point, minimum value of input DC point will be governed by the minimum DC potential allowed here, which is VGC minus VT plus VGS, and which is close to 0.6 volt, assuming this rough numbers that okay, V overdrive is lower than 100 millivolt, 0.1 volt, and VGS is close to VT, which is say 0.4 volt. So, I am just taking rough numbers and telling you that overall the minimum DC level that you can have at the input is 0.5 volt, close to that, in order to allow maximum possible swing. But for maximum possible swing, the allowed or the desired output DC level is 1 volt. But that 1 volt, if I put it over here, definitely it violates my condition, means it is much higher than the minimum DC potential that I can apply. So, that is not going to let me maximize the swing at the output.
So, what about
so, bandwidth, if I look at the overall response, you are having the total bandwidth after compensation, even if you add CC, the total bandwidth is given by GM RO square. So, if I look at the overall C value, so what is that? CC times the GM RO square, this is the pole overall. So, if you compare it with what happens with the two stage op amp when you are having compensation, there also ultimately this is your cascode, and two stage also you are having the RO and you are having the gain factor GM RO and you are having the CC. So, the bandwidth is it can be similar both the cases. Any other question? Any other question before we go to the next module? All right. So, the main takeaway from this is you should understand the advantages of this particular scheme and the limitations that we are going to solve using the folded cascode scheme, and then look at the biasing and other analysis in terms of frequency response, noise, etc. So, let us take a 2-minute break, and after that we will start the next module.